So our last presenter before lunch is MENGESHA, and Miljan comes to us from the School of Earth Sciences at Addis Ababa University in Ethiopia, and here at Michigan. He's been working in the lab of Naomi Levin from Earth and Environmental Sciences in the College of Literature Sciences and the Arts. Miljan's research is rather technical, but at the same time, I think it's both interesting and important, and he will talk to us today about his work on oxygen isotopes in soil and what they can tell us about the past environmental conditions in Africa. So we're staying with climate, but unlike Stephen, who was projecting into the future, we're now going to look at the climate in the far past. Miljan.
Thank you, everyone, and good afternoon. As my name is indicated, I'm Miljan Alamayo, MENGESHA from Addis Ababa University. This afternoon, I'm going to talk about triple oxygen isotope measurements of soil carbonates to trace past climatic conditions, specifically in the eastern part of Africa, Awash, and the Turkana bases. So Stefan has talked about the future climates a little bit, and Fauzi has talked about the past time, up until 5 or 10,000 years, and I'll take it back to 5 million years, and we'll talk about the past climatic condition. So, is this thing working? Okay. As an introduction, as I give you some information, I'm going to talk about paleoenvironment, what happened in the past. So as a geologist, we work with geological records, either fossil, either rock or something. So the study of these materials has given us that the past environment has changed over the past 5 million years. So at around 5 million years, the East African region was wooded closed canopy environment. And from that point on, it started to open up, the canopy started to open up and become grassier, open grassland. So along with this paleoenvironmental change, we have recognized the significant or major events in the human evolution. So while it was closed canopy woodland environment, the early primate we had, the early hominid fossils, used to be more like ape-like animals, and they used to be moving in quadrupedal manner, jumping from tree to tree, using their hands and legs, 4 legs. But using the change in environment towards the open grassland, the movement has to happen on the ground. So they had to stand upright, and they had to make the first step. So they become bipedal. And when they move, they browse around the grassland in the open environment, they had to adapt to the different competition they had. So that adaptation process has resulted in the evolution, in the change towards their behavior, their anatomical structure. So you can see also from ape-like morphology, it becomes more to human. The adaptation process, the change in behavior has resulted in the growth of the brain size, and what you see here as a human, we have a larger brain. And also you can see that the change in environment has resulted in the difference in tooth enamel. In the past, the canine of the primates used to be larger, but through time it gets shorter and shorter. The way they eat, the way they diet was different, so it becomes different. So that is why we need to study the paleoenvironment to understand our past. So it will help us better understand about the future, what's going to happen if the climate changes. How are we going to adapt? How is it going to change us? So how do we know the environment has changed in the past? So we look into the geological records. Those geological records are, as I mentioned, geological materials, fossils, rocks, soils, and the likes. So for these projects, I'm going to look into the past the ancient soil materials that have been deposited and covered. So in these soil materials, there are some carbonate materials, precipitated or formed carbonate minerals within the soil. So these materials will record the climatic condition at the surface. So by analyzing the carbon isotope and the oxygen isotope, we will be able to tell the vegetation of that area. We can tell the environmental or the climatic condition using the oxygen. So carbon has 12 and 13 mass, different masses, the isotopic composition. Oxygen has 16, 17, and 18. By studying the ratio of these isotopes, we will represent them in delta notation by comparing them to a standard value, either delta 13C, delta 18O, or delta 17O. We will be able to determine what has changed in the past. So our focus of the study is going to be the East African region. These stars indicate the different paleontological sites around Africa. Specifically, the Eastern Africa region is very important because most of the fossil finds we know that helps us to understand the past human evolution are found in this region. So starting from Ardipithecus ramidus, Australopithecus afarensis, Homo habilis, you can find them all in this region. And we have almost a complete geological record. So it makes sense to do our study in this area. So we will specifically focus on the Omo Turkana Basin, neighboring country to Kenya, and the Afar region of Ethiopia. So the study of the stable isotope in terms of carbon of the sediments collected from this region, the vertical axis shows us the time interval from 5 million years up until the recent. And the horizontal axis gives us the delta 13C composition of the carbon. It's the soil carbon. It's those little things within the soil. So in the past, from 5 million years to the present, the delta 13C value shows a slight increase, a shift from the left to the right, from the from the closed canopy towards the grassland. The environment has changed. And due to adaptation, the human evolution has also shifted towards surviving in this environment. We can see there is a shift. And also the Awash samples from the Ethiopian region, has represented by the yellow, shows higher delta 13C values. So some researchers have looked into this information and they have decided that the lower delta 13C value is a wet environment and the higher delta 13C value is a dry environment. Is it that simple? Is that dry or wet environment? If we look into only the carbon 13 values, that's what we are going to say. But we need to constrain further this information because the open canopy, closed canopy environment will be dependent on some climatic drivers and non-climatic drivers, not only dry and wet, but also the atmospheric carbon dioxide will have an influence into that. The temperature, the seasonality will play a role. So we cannot trace those information using only carbon. We need to have another alternative. That's where the idea of oxygen isotope geochemistry comes in to answer some climatic conditions. What will be the contribution of this isotope? So we need to understand how the system works in terms of oxygen isotope. So the system, the formation of the soil carbonates represented by the white circles is dependent on the soil water, the water we are going to find within the soil, and also the temperature during that time of formation. The measurement we are going to get from those carbonates will be the delta 18O of the soil carbonate. But we don't have the water composition and also the temperature. We have one known value, but two unknowns. in the past, we used to assume either of the soil water or the temperature to estimate what the delta 18 or the oxygen composition of the ancient water. So the water can be associated with the climate, but we had to assume. But now, the emergence of clamped isotope thermometry can help us measure the temperature directly. So we can substitute the temperature, so we have 2 known values and 1 unknown. But again, the soil water of those materials is a function of the delta 18 or the oxygen composition of the rainwater, and also evaporation. The delta 18 measurements will not give us the signature of the evaporation, how much that water body has evaporated. If we need to understand the climate, we need to constrain that information. Just by looking at the delta 18, we will not be able to determine that because it is affected by the evaporation, also the transpiration of the plants. That's when the idea or the method of delta 17O comes in. So when we look at the delta 18 of the carbonates, again, just like the carbon 30 values, vertically the time and horizontally the values, the Afar carbonates show more or less a uniform pattern throughout the time. They don't show much of a change. But when we come to the Turkana samples, up until 2 million years, they go along with the Afar sediments, the Afar samples, but at 2 million years, they start to shift towards the right. What happened? Because in the delta 13C value, we have seen they follow similar trend, but the oxygen tells us different at around 2 million years. What is that shift? So we have to look into other information. The clamped isotope information gives us the temperature of those samples. Even the temperature range is more or less similar throughout the time it's comparable for both basins. But we see there is a shift in the oxygen, the delta oxygen isotope. So we have to look into other methodology. We have to apply the triple oxygen measurements in order to constrain that evaporation. Because if we know how evaporated the water is, we can retrace, we can strip back the influence of evaporation, so we can understand the climatic condition, the real climatic condition of those water bodies. So the way we do that is we plot the delta 18O versus the delta 17O to understand that. Normally, they have almost a 1-to-2 relationship, delta 18O, the oxygen 17, and the oxygen 18. So they fall along on this line if we don't have any evaporation. But whenever we have evaporation, the graph will deviate into this kinetic evaporation. So the difference between no evaporation line and an evaporation line, we will have some excess that will be represented by cap 17O. So we can measure using the technique that has been developed by some researchers. And the audience should know that the University of Michigan at the IsoPaleo lab is one of the very few laboratories that has these high precision measurements in the world. So this measurement is very precise and it has to capture very detailed measurements, these excess values. So we had to use some robots to help us in the lab, and we can trace the evaporation along the trend. So what we do is we plot it along the excess value, the deviation from the unevaporated water. That will be represented by this line. The evaporation will fall on this line. So the data we have, this data shows us the delta 17O and delta 18O. It will fall on the terrestrial fractionation line, but we cannot see it on this graph because the difference between the two is very minute. So we had to replot it in the cap 17 into delta 18. So the unevaporated water will fall on this line. The evaporated water will fall on this trend. So now we can magnify, we can zoom into the data, and we can trace the evaporation for individual samples. So we can see that the majority of the Turkana samples, represented by the green, looks to be more evaporated than the Afar samples. That's what we see on that trajectory, that deviation on the delta 18 measurements. So we can constrain the evaporation. If we have this evaporation, we can trace back. We can stripe the evaporation. We can determine the unevaporated water, so we can determine the climatic condition during that time. And that is the data we have. And we have tried to see how that is compared to other studies. As I mentioned, the lab we have is very special, and many studies hasn't been done on this topic. So the data we have are very much limited. And we have compared it with the modern soil carbonate analysis in Serengeti, and we have seen some relationship that the Serengeti samples represented by the gray triangle correspond to the Afar samples, some of them, and some of them they have different trajectory. And also when we looked into the relationship or how it compared with the modern Afar samples, we see that the modern Afar samples is having a bit of higher delta 18O value than the past that is represented by the yellow. So we can tell that the modern and the past environment has different oxygen isotopic composition. So that means there was a change in time in terms of climatic conditions. We can stripe back and get the unevaporated water, so we can determine what was the climatic condition. So as a conclusion, stable isotope analysis is an important tool to understand past climatic conditions. We have seen that the Eastern Africa region has gotten grassier from closed canopy to open canopy in the last 5 million years. The delta 18O measurement of soil carbonates need more constraints in terms of evaporation. To constrain this evaporation, I just have shown you that the triple oxygen isotope measurement is a very powerful tool to trace back or to stripe back the evaporation trend. That's what we have done. And I would like to thank the African Study Center for this opportunity for me to come here and work on this project. I also like to extend my appreciation to my host, Naomi Levin, who has been very helpful in every way possible. The IsoPaleo lab, whose picture is given at the bottom section, the Addis Ababa University, my home institution, and also Richard and Catherine Wandorf, who have been very welcoming for us, generous for us to have the Michigan experience. Thank you very much. Go Blue. And if you have any question.
Thank you. Thank you, Million. So question time. I don't know, where are the cubes? Throw the cube to behind you, and please state your name and then ask your question.
Sure. Victor Mensa, Michigan Medicine. I have a question. As you go back,
lift up the cube.
Oh, sorry.
Yeah.
How's that? Is that better? So as you go back 5 million years and you go up to 2 million years, if in the 2 millionth year there was some volcanic activity, would that affect the isotopic composition of what happened 5 million years ago?
Definitely. If it contributes to the oxygen input, it will affect. But this time around, when we do this analysis, we are trying to trace the carbon in the oxygen. So it will not provide much information, but it will contribute to the carbon dioxide into the atmosphere. That can be recorded to the sediments.
Great talk. I liked it.
All right.
Other questions? And our Zoom person is taking care of lunch. We're not going to have questions on Zoom. So come on, in-person audience. I warned you before Million started to speak, it's going to be technical, but it was, I think, very well presented and accessible.
Yeah.
Naomi.
Hi there, my name is Naomi Andre, and I'm with the ASC. Thank you so much, and this is certainly way out of my normal wheelhouse of what I think about, but I want to make sure I understood what you said and sort of ask a question about something very early on. You said that because this area is a region where you have sort of early life and sort of from the chimpanzee sort of moving through the different...
The primates, yeah.
Yes, thank you. Aren't there other parts of the continent that also have these early forms? I'm thinking of what is frequently called the cradle of humanity down in the Johannesburg region.
South Africa, yes. I have provided the information on this slide that these stars indicate the paleontological sites where...
Okay. Oh, thanks. There it is.
Yeah, there is...
I was looking at the skulls.
Yeah.
Thank you.
Australopithecus africanus is found in the southern African region, and Sahelanthropus is found in Chad, except for this specific. You can find the other fossil hominid fossils only in this region, Ethiopia, Kenya, and Tanzania. That's why this area is very much interesting in terms of human evolution studies and Paleoenvironment analysis. So we can understand the past and we can predict what's going to happen in the future.
Thank you. And so you're looking at sort of focusing on that one area because you have a lot of them, but there are these few other areas also.
Yeah, if we can make a study in this area and in this area, but we don't have a complete record like
Thank you.
this region. That's why.
Other questions from our in-person audience? Well then, let me put a question to you, Million. So you showed us that video of the computer moving the samples around, and I'm assuming that's a video here from the Levin lab at Michigan, right?
Yep.
So when you go back to Ethiopia, will you be able to continue this work? Do you have a lab there that does this, or is this also going to be an ongoing collaboration to make sure that it can continue happening?
It has to be on collaboration because the analytical technique that is available for this method is very sophisticated, and it has to be high precision measurements. I have shown you that it's not going forward. So what it does is it tries to, if we plot our data in this graph, delta 17.0 and delta 18.0, we will not see any difference. Everything will fall on this graph. So to see the deviation from this fractionation line to this one, we need to have a very powerful and high precision measurements. That we don't have, so we have to rely on the collaboration. So that's what I'm hoping to continue with Naomi Levin.
So can you maybe just talk us through what we saw in these two little videos?
Okay. So what we do in the lab is the sample I showed you earlier has to go through the extraction phase. Just extraction to get the gas, the material we need for the measurement, it has to go through a 3-hour long process of extraction. So the working material is carbonate. The carbonate has to be digested in the acid to liberate carbon dioxide from it. That carbon dioxide has to go through a reduction phase to liberate the oxygen from it. So after liberating the oxygen, we form water. That water has to go through fluorination stage so we can get only the oxygen. So this lab, the one you see in blue, are low temperature dewars. It tries to cool the sample. The one you see at the white wrapped dewars, they try to heat, and they are high temperature up until 560 degrees centigrade. So it is a cooling and warming process. So it is a 3-hour long process. So this robot is helping us to get the oxygen out of the carbonate. Then we can send into the mass spec, which is visible around here. Then we can start the measurements. So only the extraction phase takes like 3 hours.
And then this one?
Is a liquid nitrogen. So this specific dewar has a negative 20 degrees centigrade. So it traps the water that is coming from the acid digestion. So it cools the sample down. Only the material we need will pass, and the waste or the contamination will be prevented from the passing.
Somebody throw a cube over to that corner. Thank you.
Hi, I'm Katie Wandoff. I'm just curious, prior to coming up here to University of Michigan, if you didn't have that kind of lab and machinery, how were you, what were you doing in terms of trying to get the data?
Information.
Yeah.
So the way we do interpreting the past environment, it can be done physically, observing the materials, how the materials looks, the fossil looks, in terms of, let's say, if they are formed in a high energy environment, the materials will be coarser, bigger. If they are formed in low energy material environment, they will be very finer. So by analyzing the physical characteristics of the materials, we can make those interpretations in a broader or in a general manner, the environment in which it was formed. But for climatic studies, we need to do the stable isotope analysis. We need this kind of machine. So in the past, what we do is we send the sample out for the labs who has the capacity to make these measurements.
Somebody wants the privilege of the last question. Okay, get a cube to Lare behind you.
Thank you very much. Highly technical, and I know little or nothing about what you are talking about. But I want to take you back to the maps. Mm-hmm. Yes, I wanted to know whether there was any form of interaction or migration during this period that you described, particularly from the lower part of the continent to East Africa and West.
In the West, what makes this area interesting is because there might be a chance of, having these fossils in the other part of the region. But the sediments that can possibly host these materials are not exposed. So in this area, we have an exposure. A river coming through these sediments of accumulation, it will expose the materials out. So we have the exposure, we have the materials, but we haven't found, except in the Chad region, we haven't found those kind of sediments to justify or to tell about.
I think Omalare's question, if I might try to interpret it, is, was there any migration from south to east to west? I mean, there's this huge gap in between. Is there what happens in that gap in between?
What happens in between?
There is definitely migration every now and then. So there are different time intervals in which we know there has been a migration from the East Africa region throughout the world. And also, for example, in Chad, what we have found, the oldest hominid fossil is this one, Sahelanthropus, around 7 to 6 million years. So if our starting point is this species, it has to go from this place to this place. So there is definitely a migration, there is definitely a movement in this area.
Thank you, Million.
You're welcome. And thank you.